All right, here we got lesson 2.1.2. This one is called comparing the change in y and the change in x. This little triangle is the Greek symbol delta, and in math and actually in a lot of the sciences like physics, it stands for change. So the change in y and the change in the x values. So we're going to be looking at how the x is changing and how the y is changing and how they're related to each other. So first, we're going to go ahead and graph this one that we've got here. We've got figure 0 has 2 tiles, so I'm going to go 0, 2. Looks like everything is done in 2s here. And then in figure 1, we've got 7, so we're going to go 1 and 7. Since these are done in 2s, then this would be right in the middle right there. All right, the next one is going to be at 212. So 212 goes about here. And then our next one is 317. So again, we got to go halfway because these are done in 2s. Each of these grid lines is a 2. And then we got 422. So we're going to go 422, which will be right here. All right, what I have created here is what's called a discrete graph. In discrete graph, we assume that only the points on the graph can be solutions. So maybe this is some kind of figure in tile numbers where we can't have like fractions of tiles, like we can't have a figure 0.5 or we can't have a figure 1.8 or something. So this would be a discrete graph to show us that in our pattern, only whole number figure numbers would work. Now, if we decided to instead draw a line through it, now what we're saying is that not only do each of these figure numbers work for 0, 1, 2, 3, and 4, but the fractional figure numbers also work, like 0.5 would give us an answer, and even the negatives would give an answer because we got an arrow pointing there. That's what we call continuous. So fractions of the tiles are possible, represented by any point in the line. We've already looked at some in the last unit that did that. So the line means that the fractions are okay, whereas the discrete graph, if it were only points, is saying that only the figure numbers and their tiles would work. You might use that like if your graph was representing people, you can't have half a person or a third of a person. So we would just leave it like that. So there we go. We've got our graph. Let's see if we can write an equation from our graph. Remember, when we describe our functions, we describe where they're starting. So we would say that this one starts at 2. So my description would be this function at figure 0 starts at 2 tiles. And then we talk about how it's increasing. And we can see how it's increasing here. For every one figure number that it's increasing by 5 tiles. So our description would then be first starting what the figure number 0 is. At figure 0, we have 2 tiles. And then for each increase in the figures, we are increasing by 5 tiles. That's our description. That description also helps us write the equation for this one. Okay, so let's go ahead down to the next one. Is this a function? Okay, remember, for a function, we have to have for every x value, there can only be one y value. And we can see here, for this x value, there's only one y value. For this x value, there's only one y value. For this x value, there's only one y value. Everywhere we go, there's only one y value for each x value. So yes, we would say it's a function. And since it's a function, we're going to write an equation for it. So we would say f of x, remember this stands for y, so this is the number of tiles. The number of tiles is equal to, well, we started off at 2, so I'm going to put plus 2 over here. So when there are 0 figure numbers, there are 2 tiles. X is the figure number, and we have to decide how many figure numbers is, or how many tiles is it increasing by for each figure number. and we said it was increasing by 5 each time, and it keeps on doing that. It's the same pattern over and over and over again. So we would say 5 for each figure number plus 2 to start off with. And if you plug in any of these figure numbers into this, you'll get the number of tiles out of it. All right, let's move on. Next, we've got 3 different graphs, and we want to describe the graphs and then write an equation for each of them. I'll do the first one for you, then I'll pause and I'll let you do the other ones. All right, so I'm going to describe this one. How do I describe it? Well, I start by saying how it's starting at the 0. So it looks like at figure number 0, there are 3 tiles. So at figure 0, there are 3 tiles. And then we have to describe the growth from there. It looks when we grow one figure number, we are increasing 2 tiles here. So then we're going to say for every figure, the tiles increase by 2. Almost ran out of room there. All right, now we need to write an equation. Just like the last one, the 3 is the number out here where we're starting with. That's our starting value. And then the 2 is the number that goes in front of the x for this. So I would say this is f of x is equal to, it's increasing by 2 each time, so 2 times the pattern, and then plus 3 because that's where we started. All right, so at this point, I want you to go ahead and do the same thing for graphs B and graph C. I'm going to go ahead and pause it here. So go ahead and pause yours, and then I'll show you what my answers were. All right, pause. All right, so here's my answers. On the first one, it looks like we were starting at 9. So at figure 0, there are 9 tiles. And then over here it says, okay, we're going over 1, so we're increasing by 1. And it looks like the tiles are increasing by 12. So for every figure, the tiles are increasing by 12. So my function would be f of x equals 12x plus 9. For the next one, it looks like right here that, that at figure number 0, there are 3 tiles. And then it just goes, for every increase, it looks like it's only increasing by 1 tile. And so my equation was f of x equals x plus 3. I didn't write the 1 there because usually when you have a coefficient, the number in front of x, so when you have a coefficient of 1, you don't have to write it down, but if you wrote 1x plus 3, that is acceptable as well. But x plus 3 is the same as 1x plus 3. All right, let's go to the next one. All right, so on this one, we want to look and see how this tile pattern is growing. So in this one, it looks like they skip a little bit. It looks like they're saying for every 3 figure numbers, the tile pattern goes from 31 to 58, which is 27. So we've got for every 3, it increases by 27. So we want to find out, how is that thing growing if it's growing by 3? Because usually we do it by 1s, but this one's doing it by 3s. So for this one, our question is, how is the line growing? How many tiles are added each time the figure number is increased by only 1? So I want to know, how much is it increasing by 1? Well, right now, I know that it increases by 27 for every 3 tiles, or for every 3 patterns, sorry. It increases by 27 tiles per 3 figure numbers. So if I reduce this, I would get 9 tiles for every one figure. So the rate that it's increasing is for every one figure number, it's increasing 9 tiles. So what would be the equation for this? Well, it'll be a little bit harder because look, it goes down to the negative. So we could go ahead and keep on doing that, and we could kind of go backwards now that we know that. So if you're feeling saucy today and you want to find out what the equation is, you can go ahead and start working backwards. If we know what it's working forwards, we should be able to find out what it's working backwards. You can kind of find out what it's going to be. All right, so let's move on to the next section. Next section. Now we're going to talk about what we've actually been doing here. We've been looking at what's called slope. Now, slope is a measurement of the steepness of the line. So slope measures the steepness of the line. So what we would expect is if slope is measuring how steep the line is, the bigger the slope, the steeper the line. So the closer it is to being a flat line, we would expect that to mean that it's closer to 0. The closer it is to a vertical line, that's how it gets closer and closer to infinity, the closer it gets to a vertical line. So we call the slope the change in y. We kind of saw that on that last one. Slope is the change in the y values divided by the change in the x values. So looking at this one, we can see that the change in the x values here is 1, 2, 3, 4. So it's changing by 4. So I'm going to put 4 in the denominator. And the y values are changing by 1, 2. So our slope for this one would be 1 over 2. That describes how steep the line is. Now, if I had another line that had a slope of 5, we would know right away that that one's going to be a steeper line because 5 is greater than 1/2, and since slope measures the steepness of a line, a bigger slope means a steeper line. So 1/2 means this line isn't that steep. So let's go ahead and write an equation for this one. So on this one, we now see that the intersection point here, this y-intercept, is 2. So that's when we have a figure number of 0. We have 2 tiles there. So this one would be f of x equals 1/2 of x, because that's the slope, and then plus the starting point of 2. So this is saying for every 2 increases of the figure number, we're increasing by 1 on the tiles. Now, if we just checked and saw what the slope would be, and we call these slope triangles here. So this change in y over, or change in x and change in y, we call this a slope triangle. So we would say, okay, this was +4, this one would be +2, and so we do 2 over 4 to find that slope. But let's look at just a 1-unit increase. Let's do a slope triangle from here to here. So here's my change in x, and that's a change in x of +1. My change in y becomes 0.5 because I'm going from 4 to 4.5. So this is 0.5. And 0.5 over 1 is still 1/2 because 1/2 is 0.5. So these two things are the same because it's equal to 0.5 as a decimal number. So these are giving us the same exact slopes no matter which points we're picking on the line. We could even go make a slope triangle here. I'm going to go over 2. So here's a new slope triangle. So I'm increasing by 2 here, and the y is increasing by 1 there, so 1 over 2. So I'm getting the same exact slope no matter which slope triangle I'm making on that graph. So we're always going to be comparing the change in y over the change in x for slope. All right, 2 more problems and we're done with this. All right, so we've got 3 different slope triangles here. Slope triangle A, B, and C. So slope is the change in y divided by the change in x. So let's do it for A. For A, the slope triangle, the change in y is positive 6. It's going up 6. And the change in x is increasing by 4. So we get 6 over 4. Let's look at the slope of B. Slope triangle B says the change in y divided by the change in x. Y is changing by 3. And it's changing by 3 for every 2 changes in the x. Let's do C. We're going to do the change in y divided by the change in x. So this one, it looks like the change in the x value, it's increasing by 3. And I didn't write down what the change in the y is. It looks like it's going up 1, 2, 3, 4.5, so 4.5. All right, let's reduce all of these. This is reduced to 3 over 2, which is 1.5. This one is fully reduced, but it's the same thing if you plug it into your calculators as 1.5. And how many times does 3 go into 4.5? 1.5. So we see here that no matter what we did, no matter which slope triangle that we chose, we got the same value for the slope. So what do we notice? We notice that the slope is constant on a line. Now what does that mean? Constant means it doesn't change. So in this particular problem, we've seen that no matter which slope triangle we made, and we can even make a slope triangle that does the entire pattern in here, no matter which 2 points that we pick to make a slope triangle from, we'll notice that the slope is going to be constant because on a line, the slope doesn't change. Because look at this, the steepness of that line is not changing. So it makes sense that the slope would not change. From any point, the steepness just stays the same. So that means the slope should stay the same because the slope is the steepness of the line. All right, last problem. Here we go. So Cynthia believes that the change in the y value on this one should be 3 because look at the triangle. That's 3 tall right there for the change in y. But Essie comes along and she thinks that the change in y is negative 3 because she sees that the height is 3 here, but then she says that it slants downward from left to right, so that should be a negative for it. So who is correct? Who do you think? Probably the one with the most words. Yeah, so Essie. So Essie's correct. Because if the slope is describing how steep the line is, this one, and from left to right, this one is not going up, it's going down. So it has a negative slope, because negative slopes mean that it goes down. So what's our equation of our line? Okay, well, we start with our number of tiles at figure 0. So there are 9 tiles at figure 0. And then how much is it increasing by? Well, let's look at our slope. It goes down 1, 2, 3, so that's negative 3, and it goes over 1, 2, 3, 1, 2, 3, 4. So it looks like our slope would be negative 3 over 4. So what's our equation? Our equation would be f of x equals, we're starting at 9, so I'm going to put a plus 9 at the end here. And then the number in front of x we're finding out now is just the slope value. So our slope value is negative 3 over 4. So this would be negative 3/4 x plus 9. All right, notice how I put the negative on top. So I put negative 3 over 4, but it doesn't matter where the negative is. I could have put the negative out front, so that it's negative 3/4, and that's the same thing. You can even put the negative on the bottom, but usually people don't do that. All three of these are the same thing. That's all I got for you. Go do your homework. Make me proud. All right, bye.